Hi, everyone. Welcome to this webinar with iMotions and SmartEye. We're so happy to have everyone here. Thanks for joining. I have with me Nam and Sebastian, who are going to introduce themselves, but I just wanted to give you a quick housekeeping note that this webinar is being recorded, so you will receive it in your email automatically in 24 hours. Also, if anyone has missed the webinar and they couldn't make it, as long as they've signed up and have the registration in their email, they'll still get a copy. So no worries about that. Also, if you have questions over the course of the hour, please put them into the message box that should be on the side of your screen. There's a little snapshot of it on your screen there as an example. And if you submit your questions there, we're going to be taking a Q&A towards the end of the webinar. So just drop your questions in and then I'll be moderating them over the course of the hour, and I'll be asking them live to Nam and Sebastian. So yeah, just put them in and we'll get to them. And on that note, I'm going to turn my camera off and let these guys take it away. So thanks, everyone.
Thank you, Kate. Hello, ladies and gentlemen, and welcome to this next installment of the iMotions webinar series. Today, I'm super excited because we'll be able to present some really cool topics on the advanced eye tracking methodology. And with us today, we have our eye tracking partners over there, and Sebastian Johansson from SmartEye will be joining us and providing some of the really cool insights about some of the technologies that they'll be using and some of the approaches that they worked in to overcome some of the challenges in advanced eye tracking applications, from things like simulation to automotive. And hopefully by the end of this, you'll have a better understanding of actually what's currently possible in the world of eye tracking and eye tracking analytics. But before we go into the cases, let me introduce myself. So hi, my name is Nguyen, and I've been with iMotions for 4 years now out of the Boston office, where I serve as a neuroscience product specialist. And I've been lucky enough to work with our clients and help them get the most out of incorporating different types of biosensors, including eye tracking, EEG brain waves, GSR, heart rate, respiration, and things like that, in a variety of different use case areas, including academic laboratories, to industry, automotive design, gaming companies, to government and military. Along with us today, we have Sebastian, as I mentioned earlier. Sebastian, can you introduce yourself?
Yeah, my name is Sebastian. I've been with SmartEye for about 6 years, and working both pre and after sales has allowed me to experience eye tracking in anything from the simplest to the most complex environments you can run into.
So on the agenda today, we're going to be first covering just a very quick introduction into eye tracking for those of you that are newer to this topic. And then we'll be jumping into what are the challenges as you move beyond a very basic eye tracking setup that you might be familiar with into areas that you might not know of as actually possible, and how to actually overcome some of those challenges and what SmartEye has done with their technology and software to meet that. Hopefully we'll give you some ideas about what's possible with the current technologies today, as well as where we might be actually going to in the future. We'll take a look at an example of a really extremely demanding environment, and then after we look at that, we'll have some time for questions and answers at the end. So first, before we get into the use cases, it might be helpful just to see where we're coming from. So iMotions and SmartEye are great partners in terms of providing eye tracking solutions to a variety of clients, because we have two pieces of the puzzle. SmartEye is able to provide some of the latest and greatest and best-in-class sensors out there to perform high precision eye tracking in a variety of environments, from just standard one-screen scenarios all the way up to enterprise level solutions that are out there. And they're able to do this by integrating their tools to make it very free in a variety of different platforms out there, from simulators, cockpits, airline designs, which we'll cover later. And then iMotions is able to take that information and help the researchers create their research programs by providing things like recording sessions, the ability to analyze the data and come up with insights in various ways, the ability to create data visualizations to drive those insights and provide that for their clients, as well as the ability to add various biosensors. And we're talking things like eye tracking, brainwave technology, if you're looking to try to look at things like arousals and workload, cognitive workload, to give skin response or muscle tension, to look at the way that they're responding in those types of environments in order to drive like insights and responses, and perhaps even in the future, smart technologies that actually take advantage of how people are experiencing different types of simulators or vehicles. Do you have anything to add on to that, Sebastian?
No, it covers it pretty well.
Awesome. So if you're not already familiar with eye tracking or iMotions as a software, this is iMotions in a nutshell. We're able to take from a variety of different hardware partners, including our awesome partners over there at SmartEye with the eye tracking information, combine that with other types of tools such as GSR, facial expressions through a camera, EEG devices, and such like that. And then we're able to synchronize that with other types of information. So whether you're presenting images or videos on the screen, information in from a third-party webcam, such as we do with SmartEye, or other types of environments that might be available to you, such as VR out there. We centralize that into one location to make it easy for you to process and visualize everything at the same time. And then we're able to provide a variety of different types of analytics, including real-time analysis and live viewing, different types of signal processing and analysis tools, to our ability to do annotations, post imports, markup data, export all the information raw for you to work with. And if you have custom applications, which are oftentimes the case with these advanced tools, we're able to take in advanced sensors with our API here, which is able to bring in custom information from, say, sensors that you create or simulations that you create, as well as have an API that can then forward the biological data back out for your systems to actually take advantage of it, thereby creating systems that can then respond how people are actually experiencing. And because we work with such a wide variety of applications, such as the different tool sets that SmartEye provides, we're able to do eye tracking in a huge variety of different environments. So we're talking like, in stores or in devices, inside vehicles and simulation tools out there, as well as virtual reality and gaming. And the insights that we've been able to gain from going out to all these different clients have given us a lot of lessons learned, and we'll hopefully be able to provide a little bit of insights in some of the challenges and solutions that are out there to meet some of these more advanced eye tracking scenarios. Sebastian, can you introduce us on SmartEye? Thank you.
Yeah, absolutely. SmartEye is a Swedish eye tracking company founded about 20 years ago in Gothenburg. Our headquarters are still located in Gothenburg, but we now also have offices in the US, Japan, and China. We are about 150 full-time employees, working mainly in two business units: automotive solutions, which is eye tracking software and algorithms, as well as development tools for the automotive industry, where we are currently holding 57 design wins. Then we have research instruments, which is what we're talking about today. And that's premium built-to-order systems of software, illumination, and cameras for clients that need the world's most precise measuring equipment, such as NASA, the US Air Force, and Boeing, just to mention a few. Yes, next slide.
All right, thank you. So before we dive into the first topic, why don't we take a little poll to see what everyone's experience level is. This will just kind of help us understand the best way to sort of present some of the data that's about to come up. So right now, if you, Kate, can you take away the poll, please? Yep, so we have the poll open right now. So if you go to your panel, your widget here, you should be able to open up your poll section and make the response to the question. And we'll just take a second to wait for the responses to come in. Thank you very much. And Kate, if you can let us know when we're about ready to go.
Yes, definitely. It looks like about half of you have voted, so we'll give you a few more seconds. And interestingly enough, the majority of the people voting have experience with simpler setups. So that looks like folks are not completely new to this field, which is great because, the name of this webinar is Advanced Eye Tracking. So it's great to have some people in here with experience. But if you're new to this field and want more, which looks like about a quarter of you guys are, there's definitely great insights you'll be able to get out of this webinar. And then about a third of you, a little more, are power users as well. So awesome to hear that. Thank you for voting. And that gives you, Sebastian and Nam, hopefully some insight in what kind of folks we have attending today. So I'll turn this off. And yep, thanks.
Okay, thank you so much. So, all right, so let's go ahead and dive into the application topic. So before we dive into advanced applications, there are a few of you that are newer to this. So let's go ahead and jump in the Wayback Machine real quick. So I first started doing eye tracking experiments about 18 years ago in college, long time ago, in technology terms. And when I did it, it looked very much like this type of setup that you're looking at through here. And you can see the primitive technology we had at the time, and the huge amounts of restrictions that you had to go to. We had, essentially, you had to have a chin rest where you actually had to stabilize your face. You couldn't move anywhere, and then you would have this big camera that was actually pointed at just one eye and not both eyes at that time. And that all the settings were manually set back in the day. So if you've done eye tracking in a long time, this will probably do a little bit of nostalgia for you, going in through there, setting all the different video settings and exposure settings, changing the pupil dilation thresholds that you're looking to try to get good eye tracking, just so that you can see, where on the screen specific dots were, and you can look at the size of these the monitors there. But if you're more familiar with eye tracking today, as much as you are, this is probably the type of eye tracking that you're more familiar with, which is the bar style eye tracker. And already you can see all the advantages of it. All the hardware is embedded inside. The placement of the sensor is just easy to do. You just kind of mount it on the bottom of a screen. There's no chin rest. There's no settings in terms of the thresholds and algorithms going before. All you simply do is initiate a calibration, which puts some dots on the screen, and then boom, you're right into eye tracking data collection at that moment in time. So very quick and very easy. Let's go ahead and take a look at this in action. So here I'm just doing eye tracking on a simple replay here. You can see my laptop here with that bar style eye tracker down at the bottom. I've got camera feeds turned on here, and you can actually see detecting my face. But then you actually see the readout of the eye tracker up here. If you're not already familiar with eye tracking data visualizations, what you're looking at is the eye tracking as here represented by these balls and line graphs. And then as I stop to look at an area, that ball will grow in size, which is one of the very common visualization techniques for that, known as a fixation. If you notice down here that I don't actually see these visualization when I'm actually playing this game down here, that I'm purely interacting with the game without seeing that, and that only the visualization is displayed on the secondary monitor live up here. So as a researcher, you could be monitoring what they're looking at live without interrupting their sort of pure user experience. And then eye tracking researchers that are out there, they typically use this to try to design a number of applications. In this case, it might be menu design within the games, or different types of interactions, or interactions with the other sort of mechanics as it goes through there, providing things like, is it easier to use? Is it easier to see? You might provide task-based things such as like, are people able to draw attention to the areas that I need them to go to? But the challenge is that there's a number of basic assumptions when you work with bar-based eye trackers. There's limitations on the distance from the eye tracker to the eyes as they're going into. There's certain limitations to how far you can turn your head to the size of the screen that are basic to the design of this experiment. The question then becomes, how do you then get insights into this and then apply it to more complex environments? And the insights that I mentioned are typically shown in this type of way. So you have visualizations, just as you saw earlier, such as this gaze replay, which can give you insights into things like where people look, how long they looked at it, or you can look at things like, what drove initial attention going through there. You can then collapse across the time environment and see like how people actually distribute their attention across an entire session, and see what elements actually drove more attention versus less attention. This is really important to things like design and scenarios where you're trying to draw a certain attention to a certain way. Additionally, you can draw areas of interest, which is a more quantitative method where you actually go in and actually look at statistical data, such as what was the average time spent for a group or an individual looking at an area. What's the time to first fixation, which kind of drives, what was looked at first, second, third, or fourth, to ratios of your audience. So like as an audience, how are they actually dividing their attention on average? But again, that challenge is like, this is all assuming that things appear on a screen where we know like where every pixel occurs and when it pops open on the there. So the challenge is, how do we then get this type of insights when it's not a screen where we're tracking every single occurrence and change? Environments that we're looking at now today, we'll be looking at things like this, where it's occurring in like a simulator, where like they have to look outside at a certain longer distance, or perhaps a car cabin, so that we have things like vibration, larger spaces, things that are not screened to be tracked. things that have interactions with the lighting, the changes in spaces, and as well as all the different sort of changes that can occur with objects in the background. What happens in an even simpler use case when you're just looking at multiple screens rather than just one screen? How would I do eye tracking across this type of environment? And having implications for things like commander views or command spaces where you have multiple things that are drawing your attention there. And then finally, what happens in really detailed, complex environments where it's more difficult to place an eye tracker? You don't want it to include different areas and represent these different types of things. So I'm actually going to ask Sebastian a question here. Sebastian, can you actually comment on the current state of technology that actually meets these cases that are out there?
Yeah, what you see here is basically what we at Smart Eye see on a daily basis, installing these type of systems in simulators such as the moving car simulator in the top left, instrumented vehicles out on the roads, and as well as test tracks, and also control rooms with multiple screens, and full flight simulators with co-pilot scenarios covering the full interior of the cockpit with eye tracking, as anywhere from the primary flight displays to the overhead panel, etc.
And would you say that these types of scenarios, are these like the limit of what we can do today, or are these actually more achievable environments that we're looking to try to do?
No, these are actually the more achievable ones. These are the ones we do more or less on a daily basis. We do have extreme cases with large cylindrical screens and 360-degree field of views that we need to track as well, that are not as common, but we still manage to achieve high quality tracking in those environments.
And so would you say there's almost like no limit to what you can track on, or within reason, so to speak?
Yeah, there's always limits, of course, but I would say that we do usually meet the requirements of the environments that we end up in, basically by adding or removing cameras to suit the environment that we're in.
All right, fantastic. So let's go ahead and dive into the first actual advanced setup, which is just moving beyond that single monitor. So we're just going to take one step up above that. So let me go ahead and play this example. So here we have a user here sitting in front of 3 separate monitors. And then we're just going to dive into just some of the challenges that you're already looking for. Again, with 3 monitors, you have things like, since you're not tied into a single screen, you have to be able to account for all 3 screens and the data that's being shown there. Additionally, each of these screens have different screen sizes. So if you're familiar with bar style eye trackers already, you know that they actually have a limit to the size of the screen that they can interact with. Typically, they can only go up to at most a 24 to 25 inch screen, unless you get some of the more Lamborghini level ones that are out there. And then you have challenges in terms of like the way that they're oriented. So they're not all on the same planes that are tilted in, so that get that a little bit more of a view there. So there's a lot of challenges in trying to get good and accurate eye trackings between the sizes and the orientations that are there. Sebastian, can you comment on some of these challenges and what you did to try to solve these problems?
Yeah, absolutely. So once you break the system out of the confinement of the bar tracker form factor, you're able to do so much more with it. So we can switch out the lenses to accommodate the camera to user distance of up to 3 meters, as well as placing the cameras and illuminators independent of each other on optimal locations in order to increase the field of view, but still maintain the high accuracy, and add cameras, remove cameras, etc., to cover the environment that we need. So the next slide, yeah. So what you really need to keep in mind when doing these type of setups is we need to be able to work in any lighting condition, which we do by using pattern control of IR lights to illuminate the images with high intensity but short duration bursts of light, making the system more or less insensitive to the ambient lighting. We also need everything to be synchronized, since we are dealing with a large number of cameras and illuminators. So all the cameras and illuminators are controlled by a device, allowing them to be completely synchronized during the 300 microsecond exposure time. And then every frame is time-stamped, allowing synchronization with other systems such as iMotions and other biosensors. We also need the data to be in 3D, since we install these in 3D environments, basically. And we do that by using a camera calibration method that automatically lets the cameras detect where they are relative to each other to allow us to mount the cameras as freely as possible in all directions, giving us the largest field of view possible. We then use a laser measurement tool to map a representation of that environment in 3D. So including all the objects that the subject might gaze at. What you can see on the right in the image is an example of that 3D representation with gaze, intersection, and head positioning as well.
Sebastian, can you comment on the freedom of placement that you can do with this 3D and laser combination of technology, where you can essentially place this? Is it limited to height or distance, or the number of objects that you can go into?
There are, of course, some limitations, but we can track a very large height and a very long distance. We, as I mentioned before, we add cameras based on the need, and then they vary everywhere from a single camera that can still produce data in 3D up to 8 cameras tracking a full 360-degree environment. As for the laser, that could be used to map anything from a single monitor of any size to full cockpits with cylindrical projection screens and instruments and a fully instrumented car as well. Next slide, yeah. So here we see the solution in action. So what you're seeing is basically myself being tracked by, in this case, 4 cameras. The red vector represents the gaze direction, and you should also see some white dots on my face representing the facial landmarks that we use to create and track the head model. Because head tracking is a crucial thing in our eye tracking. And this is used to calculate the gaze origin, get the head position within the 3D coordinate system that we set up to get not only 2D intersection points of the gaze, but 3D gaze data, intersection, etc. So what you can see in the world model view is basically a laptop screen and then 2 additional monitors, all being intersected with this 4-camera system. Yeah, next slide.
So how can iMotions then be challenged with taking this type of 3D data, which we had never actually done before, and actually help our clients actually generate different types of analytics in a meaningful way, and to get the types of metrics that they're looking to try to do when it's not tied to a single screen? And so the things that they were looking for were similar analytics, things like the heat maps again as AOIs, and to be able to chart those. And then additionally, they wanted to be able to add in additional biosensors, again those EEGs, the GSR, and heart rate data, in order to get a sense of the way that they were responding to those types of environments that are out there. And then finally, how to actually then work with that data so that other applications can take advantage of where people were looking and how they were responding to certain situations. And then the tips of advanced applications that they might be looking to try to do, such as detecting driver state, things like drowsy driving applications or distracted driving. Or imagine if you could have pilots being detected in terms of pilot state and when they were in stress, and have systems that actually could then mitigate or take control of certain risk factors that are going in through there. Again, as we know from experience, that those types of systems need to be perfected going in through there, but having a sense of that pilot state might be really crucial going forward in terms of the way that humans and machines then interact in the future. So when iMotions engineers and the team was first tasked with pulling data from a 3D environment, we had to try to figure out, well, what were the first things that the researchers sort of wanted out of that? And the lowest hanging fruit that we could think of was that, first off, was just that these 3D model environments that are out there, such as the 3 screens that you're looking at here, and simply just going in and saying, okay, well, what are the average eye tracking metrics looking at there? Things like time spent on each of those screens, left, right, and middle screen. Or the time to first fixation, giving us, okay, which screens did they look at first? How did they look at there? And that kind of gives just kind of a first ability to go in and output just chart data as well as normal text data that's out there. But in talking with the clients, they wanted to take the capabilities even further beyond this type of data. So how could they visualize the information interacting in a way so that they could react to changes occurring in the environment across the multiple screens that are going into there? And then how could they then create the different types of analytics and heat maps that they wanted to do in a very similar way with the single screen setup? To do that, iMotions, I'll go ahead and bring in this video here, brought in a over-the-shoulder kind of webcam view. The over-the-shoulder webcam view allowed you to then map eye tracking data from the perspective of this webcam that and here it's just placed on on a tripod behind the setup. What this allows them to do is place this in a wide variety of different situations, such as in cars. So you can imagine you can mount this in cars. You can make it stable so that the environments are never there, are never changing. And then in that way, you can then say, okay, how long do they look at different environments, different parts of the screen with this overlay there? And this was a huge challenge for the iMotions engineering team because you had to map all the different 3D perspectives that are going in through there. So how they actually, translated the world model to the perspective of this. But in doing so, they were able to then generate the ability to replay that information easily over time. And that allows clients such as trainers to be able to go in and say, okay, what are you looking at now? Why are you looking at this information? Are you looking at the correct dial going in through there? Additionally, then they could do what's known as an after action review in this type of case, where you can actually go into a replay immediately with that person, sit down together and saying like, when you were looking at this object over here, why were you paying attention to it in this situation? Thereby providing insights into different trainings, not just from the trainer's perspective, but from the trainee's perspective there as well. And from this tool, then you're able to then get those insights that you're looking to try to do before from single screen analysis, such as generating heat maps. Only now, instead of looking at it from a screen by screen perspective, you're able to look at it from the perspective of this over the shoulder viewpoint and get things like distribution of attention as they looked across the multiple objects. You can do areas of interest, and here you can see the power of it, because you're not just looking at areas of interest on a single screen, but you're able to take a single area and actually stretch it across multiple screens here in this case, which allows you to then combine that into a single metric that they're looking for and get those things like, what's the average amount of time spent for an individual, as a group, what are they looking at in terms of audience, how are they breaking down the images in terms of order and pattern and primacy there. And then able to then take those insights and easily turn them into simple visualizations, such as like averages across there, to make easy comparisons between each of the individual monitors without having to code it in a complex way. Next, we can actually then take this visualization even further. So there are certain situations that we come into play in advanced scenarios where we don't get necessarily access to the screen that is being shown, such as that it being presented on the same monitor. To meet that need for those clients, we came up with a prototype. So this again is a prototype feature of a post-import procedure, which allows you to actually bring in video files from other types of systems that are recorded and then visualize them in this sort of more command center kind of way. So in here, we are able to then, you'll be able to not just visualize it on the screen from this over-the-shoulder perspective, but as well as actually see it in live time here, as well as actually create more detailed viewpoints in this commander viewpoint view. Here then you can create the same types of analysis that you would before in terms of heat maps, areas of interest, only now you're able to do it in much finer detail and much finer control because you're able to visualize it all at once and in greater detail and focus on just the parts that you're looking for in larger aspects. And then finally, of course, you can add in the same tools that we're looking for before, such as GSR, eye tracking data, brainwave data, in order to then see, like in detail, like as they're going through and panicking, are they efficiently navigating the environment and things like that to get a better sense of what they're looking for. So next, we're going to kick up the difficulty a little bit inside an aviation simulator here. So we're actually going to play a little game first before you go into there. So, so this is the audience interaction portion of the webinar. So here we've got two images of simulators. These are actual full realization simulators where you actually sit inside of them. And these have both been outfitted with eye tracking, Smart Eye Pro eye tracking technology. So I want the audience to do is just take a minute and actually try to see if they can spot the eye trackers that are actually mounted within here. This being a helicopter simulator with the helicopter yoke and display, and this one being a standard airplane simulator. in just a few seconds here. So Sebastian, can you actually point out where the eye tracking technology is here?
Yeah, definitely. So if we start by the helicopter simulator on the left, there's actually one camera on each side of the instrument cluster right there, yeah, and the same on the opposite side with one illuminator each on top of them. There's also a camera that some of you might have missed on the top center of the instrument cluster. You could just see the reflection of the lens, basically. Moving to the airplane simulator, we have one camera under each of the primary flight displays with one illuminator on each side of it. We also have two cameras on each side of the central display area, pointing at the pilot and co-pilot with their own illuminators. There's an illuminator and a camera above the glare shield. Most of you probably spot the glowing illuminator, but the camera is a little bit harder to spot. You can just see a slight reflection from the lens there as well.
So this speaks to sort of the non-intrusiveness of this particular setup. Was that a requirement from the client in terms of having the really small footprint there, and why was it a requirement, you think?
It was absolutely a requirement, and we always encourage naturalistic behavior of the users. And to get that, you need the systems to be as unintrusive as possible. So what you see here are systems that are kind of installed and hidden in plain sight to make them as unintrusive as possible. And this is only possible due to the small footprint of the cameras and illuminators. They're not, however, fully integrated into the cockpit, so you can take this another step by hiding the cameras behind the panels and cover them with just tinted glass. And this extra step becomes very critical when moving towards certified training simulators.
So next, let's see an even more advanced setup where we try to do eye tracking on a Kraken. Now, much as I would like to say that there's a mythical creature out there that we did eye tracking on, the Kraken is actually a Navy simulator, a flight simulator that is out there. Let's go ahead and play a video of it. So Sebastian, while we're looking at this video of this flight simulator, can you comment on to what the purpose of this device was?
Absolutely. So the Kraken is basically a disorientation device built to add disorientation and that extra layer of realism to motion simulators and basically gain a better understanding of motion-related factors in moving vehicles.
So inside this simulator, there's a little cockpit that's actually being spun around, exerting different G-forces on the individual. And as you can see, there's even more axes. So it's actually spinning up and down and left and right, providing this sort of training advantages so that when pilots are in here, they're able in a safe way to deal with the different sort of G-forces and disorientation that might occur going in through there. So Sebastian, what are some of the challenges in eye tracking, doing eye tracking research in this type of environment, other than the obvious, which is just the sheer amount of movement that's going on?
Yeah, so the main challenge when installing systems like this in simulators such as this one is always to install the system in a way and find space for the system in a way that they produce the required field of view, while also being unintrusive and not covering any of the monitors or instruments or controls, basically. And in the Kraken, we also had to take into account the G-forces and constant movement and vibrations of the system. So it really puts a strain on the system.
I'm sure cabling was such a huge challenge as well. Not even just the placement of the tools, but just getting everything situated and not intrusive with the cables as well as the camera systems themselves.
Oh yeah, definitely.
Sorry, small hiccup. Let me just go ahead and get back to there. To my presentation. So when challenged with analyzing this type of data, why don't we just kind of quickly take a look at this simulated example of this. So when you're trying to analyze the information coming in from the 3D perspective, again, we're taking advantage of that same similar camera tool. Because the webcam is just a standard normal webcam that you can place anywhere, you can install that in these types of situations fairly unobtrusively as well in order to get a very similar style of results. So here we've got that 3D model as the trainee here is going through a few numbers of tasks as they go through. And then you can see the replay as he's actually looking at these different flight display areas. Additionally, we have a number of different biosensors connected to the individual, such as GSR sensor, as well as facial expression readouts here, so that the trainee can then express this information, be displayed there, and that the trainer can then take advantage of that in live times. And here we're able to then, in a complex environment where this entire gimbaled machine is able to move up and down and be exerted to different types of vibrations and G-forces, we're able to take into account, again, all that type of information and then get a sense of how that person is responding. Therein, the trainer can then take advantages of it and say, hey, you know, when an engine failure occurred, did they efficiently look at certain areas in the right order? Or if there's a prescribed standard operating procedure to go through, such as through landing, did they go through and tick off all the different tool sets, not just actually flip the switches, but did they actually look at those switches? Were there extraneous areas that they actually paid attention to that made it inefficient to what they were looking to try to do? Did they pay attention to, say, you know, areas that were just unimportant to those types of tool sets and readouts? And then finally, did they pay attention to the types of readouts in terms of the biological data? So when they're going through and exerting their things, were they panicking a lot and going in through there? So as a pilot, you don't want the person there going through to be, you know, having a panic attack each and every single time. Perhaps to train them efficiently, it would be good to make sure that they were always calm through that situation. And with our tool set, you're able to then get those additional insights into there. In addition to those things like the heat maps, the areas of interest, each of the primary flight display tools there as well. So that kind of dives into some of the basics there of eye tracking. Hopefully you learned a little bit more about some of the eye tracking applications that are possible that are out there. We're going to go ahead and take a quick poll to see if there are any follow-up questions with this audience in Q&A.
Thanks, Nam. I just launched this poll, so if you would love to hear more about Smart Eye and iMotions and all the possibilities that we've showed you just now, just take a minute to just answer this poll, and while we're doing that, we'll give you a couple minutes, but I would love to start asking you guys some questions. So Nam and Sebastian, I will just surface the first question for you guys while we have this poll going on. So we have a question about the multi-screen system. An attendee is asking, does the system need to be calibrated every time for every user, or how does that calibration actually work?
So from an eye tracking perspective, Smart Eye actually does not need you to calibrate every time for every user. You can save the profiles, and right now we're also releasing a Face ID module that will basically pick up, as long as you've been there before, it will pick you up as a user and just load your profile and gaze calibration automatically.
Although
Awesome.
that's not the recommended way of going about it. If you can at all do the calibration, please do it. It will definitely increase your accuracy. But we understand there are situations where you can't. So.
Great. It looks like the majority of people have voted now, so I'm going to close this poll and let's get some more questions. So again, if you have questions that you would like to ask Nam and Sebastian, please just put them in the chat and we'll get to you hopefully before time runs out. So next question we have is, what type of light is emitted from the burst cameras you mentioned?
So it's near IR light, so near infrared light at 850 nanometers. And again, it's for a 60 Hz system, which is the most common ones that we have. They will be illuminating 60 times per second for about 300 microseconds a time.
Great, thank you. I hope that answers that attendee's question. Cool, let's keep going on to the next one. Sorry, there's tons of questions coming in, so I'm just trying to catch up. Someone is asking, so we used 2 cameras back in 2005, and why were there 3 cameras in the setup that you guys showed?
Again, basically just to cover different environments. As I mentioned, we sometimes use just a single camera. 2 and 3 camera systems are quite common, and then again up to 8 cameras, basically depending on the field of view that's required. the larger the field of view, since we are not wearing the cameras and they don't follow us where we look, we basically need to add cameras as we turn our head in order to expand the field of view and still have high accuracy eye tracking.
Yeah, Sebastian, can you comment on exactly what's like the need for flashers and cameras per like slice of visual angle that you're looking at?
Absolutely. So the illuminators actually have two purposes. One is to basically illuminate the image. Since there are IR filters on the cameras, we only look at the light illuminated from the flashes that we have, and that's also the way that we get insensible to the surrounding light. So we want them to be positioned so that we don't cast any large shadows on the face and so on. But we also use these IR illuminators to create a reflection on the cornea that we use to triangulate the eyeball basically and create this gaze vector. And same thing here, if we turn our head too much or look too much up or down, we need to add an illuminator on that position as well. To give you an example, most of the flight cockpits that we do to get a full range of tracking is either 4 or 5 and sometimes 6 cameras, and usually up to 4 illuminators, and that covers quite a big field of view.
Great. To elaborate on that, folks are asking about things like bike riding. So how would you track these in an environment that's more like dynamic? What would be the rest, especially with areas of interest? The question is, yeah, dynamic situations, riding a bike, would the subject be followed automatically, or how do you actually make those AOIs?
I think I can take that one. So again, you need the best tools for the job. And again, when you say bike riding, what is the actual type of environment? Is this a simulated bike where they're actually stationary, such as like a Peloton style thing, where you have a virtual environment in front of them and they're actually still? And then in which case, a system like SmartEye would absolutely be available, or any of these other bar tracking ones. If, however, they're not tied to a specific computer, if they're actually on a physical bike that's actually traveling around the countryside, then you will have to leverage other types of technologies that are out there. But again, like, those technologies also have limitations in terms of things like their sample rate, the data quality. You'll have to deal with vibration because that's still not going away when you're going up and down the road. But it's still absolutely possible. But you'll have to then take into account the additional noise when you sort of move from a controlled lab-based environment to out in the wild. And so the best advice would actually be to create a research program that actually goes from one to the other, and so that you do both in order to gain insight. So you might use like a system similar to the SmartEye Pros to do one with inside a bike with a full like simulator perhaps within a cave. And then transition to some of these other technologies where you can actually go out into the to the wild there and get that noisier technology, but more environmentally valid results. Anything else to add to that, Sebastian?
Not really. Just as you mentioned, I mean, if you're in a simulator environment or a lab, then a remote system like this is perfect. But there are limitations. You can't really mount this system on a bike and go biking. I mean, anything's possible, but in those type of situations, there are better suitable systems.
Cool, thank you guys. We have a question about the data outputs, about which kind of data are available in real time. Maybe you can answer this one, and thus can be processed like during a session, and what needs to be post-processed afterwards.
Absolutely. So typically in real time, what people mostly want to look at is that gaze plot. So that actual ball like that's on the screen and where they're paying attention in time. So that replay that I showed you earlier, where you see the visualization of the saccades and fixations, and then as the fixation becomes more mature and you're looking at a longer fixation, it's either a growing ball or a changing color going in through there. That's all available for you live, as well as the readouts from all the other sensors that you might have incorporated in through there. But if you're looking to have other types of information, things like processed information like saccade length, angular velocity, and that type of nature, those can be processed afterwards in post. I believe SmartEye, if I'm correct, also has a live blink detector also there as well. Is that true? Or
yeah.
And can you actually comment to the huge variety of actual 3D modeling outputs that you're available to do live as well, which we also incorporate?
Yeah, absolutely. So as I mentioned, everything is captured in 3D. So we have anything from head position to gaze origin and gaze direction all in 3D, as well as the gaze intersection. So it's not only in 2D on an object, but it's also telling you which object you're intersecting and where on that object you're looking, basically. And all this is set up in the 3D world that we define within SmartEye Pro, and that can be altered to suit other 3D coordinate systems as well. So there are basically about 140 parameters of raw, filtered, individual per eye, which is important gaze data.
So yeah, so just to kind of summarize, from the viewpoint of that over-the-shoulder camera perspective, you get that gaze plot, and then all that raw data that Sebastian mentioned.
Yes, cool. And are there best practices that you can recommend just when you're setting up these 3D worlds? I know you covered it a little bit, but just like quick takeaways from that multi-screen setup or 3D world, what are the best ways to be able to capture that data so that it's really usable in iMotions?
So I would say that basically just accept that it takes a little bit more time to set up a remote system than it takes to just put on wearables. And if you do it carefully and you do it right, then you will have accurate and especially robust data, so that there will be minimum data loss. And again, if you just take your time and set it up the way that we advise, then I would say that that's once you do that, then the rest will follow.
From my perspective, the first thing that you need to do is just know exactly where you're looking to try to pull data from. So a lot of people try to just kind of map like larger areas of information and then say, oh, I wish I had done eye tracking data over here or eye tracking data over here. So just try to start off with the sort of the most general data, and you can always drill in tighter with our AOI tools on different specific gauges. So try to have the most general areas that you're looking to try to do, and then in post, then you can dive into the smaller ones. But always just have an idea of the types of outputs that you're looking to try to do, and then that way it'll kind of set up the design of your experiments more precisely so that you can better get the data that you're looking for.
Great, thank you both for that. A few more questions. We have about 10 minutes left, so let's see if we can run through the last few. I have a question about the accuracy in degrees for gaze mapping and eye tracking. So I would love if both of you could just answer that from both of your perspectives about accuracy and precision.
Sure. Should I start now?
Go ahead.
Yep. So from a SmartEye perspective, it is a bit hard to answer, but because it does depend on the, especially on the environment and field of view. I mean, the larger the field of view, it is of course harder to maintain the same type of accuracy as you do on a single monitor, especially if it's a small one. But generally, if it's a system that's installed correctly with the correct number of cameras that environment and field of view requires, usually about a degree of accuracy is what we can expect. And then again, of course, it varies on different individuals and that sort of thing.
I think also from my experience that the accuracy is hugely dependent on not just the equipment, but the environmental variables there as well, especially during calibration. So things like, the way that you set up your eye trackers, the dynamic events behind you can come into huge plays, such as things like lighting and such like that can have interference. And that calibration procedure, as you get in, like just, did they look at that location and the control that you have there will have oftentimes even larger effects on your resulting precision than the eye tracking rating of the devices that you're using. So you could take a super high-end eye tracker, and if you got a bad calibration, you're still not going to get good sort of matching to that environment. Is that correct, Sebastian?
Yeah, absolutely. The calibration, of course, and everything being done the way it's supposed to is of course crucial.
Yeah, that being said, the way that you have these overlapping fields of views between these different cameras, I think provides sort of a little bit of a safety net that you can have. Whereas like if you got bad eye tracking from like one camera view, you might have another one in there that is able to make up for that partial data. And yeah, I think your software is able to sort of make up for that as well, right?
Absolutely. All the cameras basically work together, providing a single data stream, and that's also what you mentioned is basically the reason why we need to add more cameras, because as you said, we might have a situation where you are covering a camera with one hand due to you controlling some instruments, or turning away from one camera, making that camera maybe not fully lose the side of your eyes and your face, but it might lose enough for it to cause bad results. So that's why we add multiple cameras.
Great. A follow-up to the question about AOIs for dynamic situations. If an object is actually changing its size in a dynamic situation, how would you cope for that on the analysis side? Because if you have, a gaze point that is actually changing in relation to the space around it, how would you solve for that?
Absolutely. So that's always a huge challenge in the way that you go into that. Obviously, there are sort of automated sort of computer vision based methods out there to actually track an object as you go through, but those are more better acclimated towards sort of sliding, where the object doesn't actually change its physical dimensions in the visual angles that much. So having objects actually grow is a big problem for computer visions, and unfortunately, it's one out there that is still sort of being solved. So the solutions that we have out there are things like manual tracking. So you actually go in and set different tools. So with things like keyframing, you're able to go in and actually have an object that actually is able to morph along with that. Additionally, you're able to provide feedback to the computer motion-related algorithms by adding in things like anchor points. So you're able to have it and help that algorithm go along with things like automated keyframing, which is also a feature that we have. If you're interested in this, we have in other webinars gone in deeper detail things like these types of tools before, such as our previous webinars on eye tracking.
Yes, that's a great point. If you want to see the recorded versions of the webinars, all you got to do is go to iMotions.com/events. We have all the recordings there that you can see for yourself. So thanks for mentioning that. We have time for 2 more questions, so I'll launch one that's sort of a like hypothetical one, and then one more practical. Let's start with a practical one. Do you find that it's possible to do eye tracking in children? And if yes, then from what age?
Yes, absolutely. So we have actually recently, in our latest release, released an infant module. So we are able to track on infants, basically. And apart from that, as soon as you get up to a few years of age, then the facial characteristics are more or less the same on a child as a grown person. So, but good question. And we do have an infant tracking module to track on infants, which we have done in the past a couple times as well. But then it has been a more manual work involved, you could say.
From an application procedure for the children and infants that I've done before in the past, the challenge is less on the technology and more than just getting them to sit still. So if you can solve that problem, then you'll get the data that you're looking for.
Yeah.
Yes, maybe time to reinstitute those chin straps.
Sometimes.
Okay, great. Last question, and then we'll say thanks for today. Question about the future of driver monitoring systems. I would just love to hear quick thoughts from both of you on where you think those are going and whether eye tracking is playing a role and what the future of that looks like.
Yeah, I mean, as long as there's going to be a steering wheel in the car, driver monitoring is going to be a thing. We do see, regulations coming into play where driver monitoring is going to be a requirement, and I think all our design wins that they speak for that as well. And there are actually cars, about to roll out with our technology. So it's definitely going to be a hot topic as long as there's a steering wheel in the car. And once you don't have a steering wheel, then it could be more for user experience, looking at controls to, user control with eye tracking and that sort of thing.
Yep, from my perspective, absolutely. I think even moving past the time and point when when steering wheels are no longer in cars, even if we move into to fully automated driving, imagine sitting in a car with a very aggressive driver. Are you comfortable driving there? Now imagine that's the robot driver. Like, would you actually keep a car that always continuously made you uncomfortable going in through there? And so being able to tell, what you're concerned about, if the car is braking too late, like, if you're sitting there with my wife and I'm all constantly kind of putting my hands on the wheels because she brakes a little bit later than I am, is definitely not a good situation going in through there. So being able to detect, how you're paying attention to, what you're sort of reacting to in terms of your physiological state, I think will always be a critical statement as technology moves beyond there. And so in making the world a safer, more productive, more faster place, and from a vehicle perspective, definitely eye tracking will play a huge role, as well as all the other biometrics possible.
Thank you. I think that's a good place to end. Do you have any final words you'd like to leave with us?
Sebastian, go ahead.
No, I just appreciate you all tuning in and checking out this webinar. And should you have any more questions, smart eye and eye tracking related, just feel free to visit our website.
Absolutely. Thank you very much. Thank you for spending some time with us and learning a little bit more about advanced eye tracking applications and what's hopefully possible now. Please visit us on LinkedIn if you're interested in learning more about our companies. If you want to have specific questions, please visit the email at marketing@imotions.com. Or if you're looking for a free custom demo, please visit the link below at imotions.com/request demo. Thank you very much, and thank you for joining us. Have a nice day.